If you're in my 5th period class, by now you should have watched 2 videos. One, the Veritasium video on Newton's third law. The other is the Hewitt video on Newton's third law. At this point, I'd like you to get out your packet. We're going to start working through the worksheet for 4.3. If you need to, pause the video and then come back. Okay, so we're going to first look, the first problem, I assume by the Veritasium video, you can answer that now. You understand that by Newton's third law, the rock is pulling on the earth just as hard as the earth pulls on the rock. What is the difference between the earth and the rock? Why is the rock accelerating, but the earth does not seem to accelerate? You should be able to answer that one. I'd like to focus on problem 2 now. We have Ramon pushing on a bed. On the side here, I'm going to draw an FBD, a free bed diagram in this case. We have the bed there in the middle, so our system is the bed. Let's look at all the forces on the bed. As we've seen with all of our free body diagrams, we have force of gravity. In this case, I'm going to say it's the earth pulling on the bed. We have an upward force. That is going to be the floor on the bed. There's a force going to the right. That would be Ramon pushing on the bed. We also have a force going to the left. That would be the wall pushing back on the bed. Now, each of these forces have an interacting force that applies to it. All these forces act in pairs. So what I'm going to do for this video, I'm going to show the interacting pairs in red here. Notice these are not part of the free body diagram. So if we have Ramon pushing on the bed, going to the left here, we've got the bed pushing back on Ramon. If the earth is pulling on the bed, we have the bed pushing back on the earth. The wall pushes on the bed. Guess what? I think at this point you should have it figured out. We've got the bed on the wall. And if the floor is pushing on the bed, we have the bed against the floor. All these interacting pairs, everything I'm showing in red here, these are not part of the free body diagram. Only the forces in blue are the free body diagram, but all the red forces are the interacting pairs that you would see from Newton's third law. Okay, let's go on to the third one. We have a bus hitting a bug. If you ever drive in the Central Valley in the early evening, you will hit lots and lots of bugs. How does the force on the bug compare to the force on the bus? At this point, you should be able to answer that. By Newton's third law, forces are equal and opposite. So why does that bug go flying along? Why does it suddenly start moving as fast as the bus while the bus doesn't come crashing to a halt? How is the acceleration of the bug so much more than the acceleration of the bus? Well, keep in mind, remember from Newton's second law, the acceleration is the force divided by the mass. How does the mass of the bus compare to the mass of the bug? That will tell you how the acceleration compares. All right, there are a series of other problems. I will just highlight a few things for you. We have a problem 4 here. We have instruments attached to a weather balloon with a mass of 8 kilograms. The balloon is released. Once it's released, it has an upward force of 98 newtons on this package of instruments. The instruments themselves have a mass of 8 kilograms, so the force of gravity, the downward force, is going to be 8 kilograms times 9.8 newtons per kilogram. That comes out to be 78.4 newtons. Net force is going to be, subtract the two forces, you'll see you have 19.6 newtons upward. And then you can find the acceleration. Acceleration is going to be net force divided by the mass. Work that out. After that, the rest of these are problems like what you had done in the previous unit. You can find the velocity of the instruments, you can find the net force acting on the instruments after they're released. Once they're cut loose, the only force acting on them is gravity, and the acceleration will be a negative 9.8 meters per second squared. Part D, we are going to say, when do they turn around? When does the velocity first become downward? That is, when does the velocity become equal to 0, given that they had been moving at a speed of 24.5 meters per second with acceleration of negative 9.8 meters per second squared. So figure that out. Grand finale, part E, I'm going to tell you, don't worry about it. I'm sure you'll happily know that you do not have to do this one. All right, so I know we are in no homework week. Seniors will have all of this will come due after next week. So do the best you can on it. I will talk to you later on. Bye-bye.